than Quantize, dominant subspace guided low rank reconstruction. We are looking at the problem of post-training quantization, PTQ, and specifically quantization error reconstruction. The standard objective in this feed is to approximate a weight matrix W, which we quantize component Q, and a low rank correction LR, such that W equals to Q plus LR. So if we go to the figure 1 in the page 3, so we can see here that the author identifies a fundamental flaw in the current state of the art methods like REST-LoRa and QERA. These methods typically quantize the full weight matrix first, calculating Q equals to KW, and then attempt to approximate the error using SVD. The author argues in the backward, if you look at figure 1, you can see the singular wave spectra of the quantization layers. In layer like up and down projection bottom row, the error spectrum is flat. This means that structure is destroyed by quantization before we try to save it. This paper proposes SSR, that is structural residual reconstruction. The intuition is extract the dominant low rank structure first, preserve it in high precision, and only quantize the residual tail. So moving on to the page 3, section 3.2, a simplified case. So that is for S equals to I. So let's get into the math. We start with the simplified case where we ignore activation outliers. So the scaling matrix S is the identity matrix, that is S equals to I. The goal is to decompose W. Instead of quantizing W directly, we take its singular value decomposition that we call as SVD. So you can see the formula here is present for the SVD. W equals to this. So here the subscript H represents the head and L represents the lower energy tail. So if we see the equation like 5 and 6 on this page, number 3, this LR and Q equations. So by doing this, we quantize the term Q has a smaller norm and reducing the absolute quantization noise. Then we compute the correction term LR. In standard methods, LR approximates random quantization noise. In SSR, LR is derived from the structure. So we are actively preserving the exact quantization inside the low rank term. We are not recovering it, we lost it. So now if we come to the section 3.3 in the page 4, the extending SSR to general case, that is S not equals to I. Now real world LLMs like have outliers. We need activation aware quantization where we can scale widths by sensitivity matrix S. If we naively apply the previous methods in the scaled space SW, it fails. Figure 3 shows SSR problem worsening than the baseline purple regions that we saw in the previous page. Why? So if we do SVD on SW, so we find directions that maximize variance in the scaled space. However, to get back the weights, we multiply by S inverse. So we can see the formula for this W array is directly proportional to S inverse SW out. So like as S inverse is large, it can amplify unimportant tail directions from the scaled space into massive errors in the weight space. So if we look at this equation, score equals to sigma I SI inverse UI. This measures how much does this direction matter in the original weight space. So now further equations we can see for the H and L. Here this leads they then identify the matrices indices H. The set is intersection of top R spectral directions and the top R contribution scores. We only preserve directions that are significant in both the activation weight view and the parameter view. The final algorithm for the general case is equation 12. Now moving forward, Prashurjya will explain.
The next section starts with QPFT and partial freezing. This method naturally extends to fine tuning. Usually LoRa initializes A is equal to 0, P is equal to random, but here our LR term already contains the dominant spectral information of the pre-trained model. If we fine tune all of it, we override that critical initialization. And then moving on to forward, the authors introduce partial freezing. They split the rank R adapter into two parts. First one is the frozen part K, which corresponds to the most dominant vectors, and these are locked. And the second part is a tunable part, R minus K, and the residual subspace. So the formula for L frozen and L tune are given in the research paper. We only calculate the gradients for L tune. This stabilizes the training by anchoring the models to its original spectral backbone. And further, we try out different experiments and trends, and let's verify this empirically. So first, the PTQ results in table 1 uses llama 2 7 billion at 3-bit quantization. Here SRR applied to QVRA exact drops perplexity from 9.17 to 9.07. It consistently improves every baseline it is added to. But the real shock is in table 2, QPFT on glue. Look at the 2-bit quantization column, the hardest setting. uh, QLoRa achieves an average score of 65.88, and QERA achieves 74.28. SRR achieves 78.82, but this is a massive gap. In the 2-bit regime, where weight structure is decimated, preserving then quantizing is the main difference between a working model and a broken one. And finally, on GSM 8K maths reasoning model, SRR achieves 38.22 accuracy in 2-bit mode compared to the 0% or 21% for competitors. It preserves the reasoning logic better than iterative models. And finally, to conclude this, the paper makes a mathematical case that the order of operations matters. By inverting the standard pipeline of doing the decomposition before the quantization, and using the contribution score to align the scale and unscaled spaces, SRR provides a mathematically superior initialization for compressed LLMs. Crucially, it allows us to push quantization down to 2 bits with usable performance, something previous methods struggled to do so. And this concludes the deep dive on SRR. And next, we will present our own results that we have reproduced in our own terms.
Preserve then quantize. The focus is to evaluate whether the key behaviors and improvements of SRR still appear under restricted hardware, smaller models, and the subset datasets. So the key difference from the original paper was the model size. In paper, it was Llama 7 billion / 13 billion parameters, and ours were a tiny Llama 1.1 billion parameter due to the VRAM limits. The hardware in paper, it was 8 times NVIDIA A100, and ours was Google Colab T4. The dataset in paper, it was the full Wikitext2 with full glue, and ours were the Wikitext2 subset plus MRPC subset. The goal, paper shows the shortest quantization, and ours were test whether the core mathematical trends still appear at the small scale. This lets us evaluate whether SRR is scale dependent or scale invariant. The method summary: for each matrix W, SRR performs thus W with and taking the top are singular values and vectors. The remaining values vectors are the tails, and it quantizes only the tails. Reconstruct as a structure residual preserves head exactly. The intuition: head is the dominant structure semantic and syntactic information, and tail is noise-like components amenable to quantization. This prevents the spectral flattening that occurs when quantization everything. We implement 2 variants, S equal to I identity scaling and direct SVD, and activation aware SRR using contribution scores. The contribution score formula was in the paper. Trend 1, the reconstruction error across layers. We first measured the Frobenius reconstruction error for SRR versus QER across the MLP up, MLP down, attention projection, and the small residual layers across ranks from 8 to 64. SRR consistently produced lower reconstruction error. This gap was largest in MLP up-down projections, same as the main paper. In tiny Llama 1.1 billion parameter, we observed that QER flattens singular spectra, and SRR preserves the top R structure and quantizes only the tail. Reconstruction becomes much more predictable. Even though the model is 1.1 billion versus the paper one was 7.7 billion, the spectral pattern is identical. The trend 2, the activation aware scoring. Without activation aware scaling, layer-wise reconstruction error was unstable, and dominant directions were sometimes ignored, and also noisy directions were mistakenly preserved. With contribution scores, the reconstruction error becomes stable across layers, and the chosen subspace aligned with important activation directions. And coming to the summary, so far we have confirmed that SRR lowers reconstruction error, activation aware scoring is crucial, and spectral behavior of tiny Llama closely matches the Llama 2-3 trends. The mechanism behind SRR is visible even at a small scale.
Now continuing with trend 3, perplexity at 3-bit. The strongest claim in the original paper is rescue effect at low bit widths. Our Wikitext2 subset results in the method for FP16, the perplexity is 18.7. For RT9 3-bit, it is 69.42. And for SRR 3-bit, it is 36.21. From this, our observations are RTN collapses completely because of text loops, malformed dependencies. SRR maintains structure, coherent English, and stable generation. The perplexity improves nearly half the zeros. This matches the original behavior reported on 7 billion and 13 billion models. So SRR's rescue effect is not scale dependent. And coming to the visual and qualitative behavior, in generation tests, RTN at 3-bit produced repetitive or degenerate text. SRR produced coherent paragraphs, correct grammar, and valid sentence boundaries. This demonstrates that preserving dominant structure stabilizes forward passes, even 3-bit quantization. And coming to trend 4, it is fine-tuned stability. The SRR paper proposed QPEFT, quantized PEFT with partial freezing. Idea is freeze the preserved dominant subspace, train only the quantized tail and LoRa adapters. On MRPC, LoRa without SRR, it gives 42% accuracy, training unstable, and oscillator loss. But with SRR plus partial freezing, it gives 60% accuracy, stable gradients, and smooth training curve. Even at small scale, freezing the preserved structure prevents the claustrophobic forgetting. Stabilizes optimization, matches the main paper's trend on glue task. And coming to hardware and memory efficiency, Tiny Llama And coming to hardware and memory efficiency, Tiny Llama 1.1 billion memory usage, FE116 1973 MB, and SRR compressed gives 431 MB. And the final result is 4.57 times the memory reduction. So from this, our key observations are: lower memory footprint is crucial for edge devices. Quantized model reduces DRAM bandwidth pressure. Our inference slowdown was due to Python reconstructing FP32 weights. Real kernels would avoid this. Memory reduction is scale invariant, so benefits extend to larger modules. And coming to latency observations, while the paper reports speeds up due to efficient kernels, our Python level implementation showed slight slowdown. Reconstruction overhead dominating runtime. No GPU kernel optimization. However, the bandwidth reductions match the original paper, showing the hardware level speedups are achievable with proper CUDA kernels. An alignment with proper original trends across all 4 core claims of the original paper. Lower reconstruction error reproduced. Activation error stability we reproduced. Rescue effect at 3-bit we reproduced. QPFT fine-tuned stability we reproduced. And this happened despite using 7 billion instead of reducing 7 billion from 1 to 1.1 billion model, and from A100 to T4 full data sets to subset data sets. This shows SRR mechanisms is fundamental, not dependent on scale or compute. And lastly, giving the implications, the fact that SRR works at small scale implies it can be applied to consumer hardware workflows. It benefits edge developments, mobile inference, and CPU based models. The mathematical reasoning is generalizable. Structure preservation is a key design principle for future quantization methods. And coming to conclusion, our 1.1 billion scale reproduction demonstrates that SRR preserves dominant structure, reduces spectral distortion, stabilizes both inference and fine tuning, reduces memory footprint by 4.5 times, improves 3-bit performance dramatically. All key trends in the original SRR paper remain consistent even in a resource constrained environment. We are happy to take questions.